Welcome to World Prism. Please subscribe and hit the bell icon for more breaking updates. In the halls of science, caution is king and data is currency. But after China's Chang'e 6 mission, Nobel laureate Dr. Evelyn Reed issued a statement that shook the astronomical community. "We have long believed the moon is a dead, predictable world," she declared. But the data from the far side forces us to admit our foundational story of planetary evolution may be wrong. The discovery wasn't just a curiosity, it was a warning. The moon, once thought stable and unchanging, still holds secrets that could unravel our most cherished theories. Dr. Reed's warning wasn't about an imminent threat, but about the unsettling realization that the universe is governed by rules more complex and violent than we imagined. The detection of a highly oxidized mineral in an oxygen-free environment suggests catastrophic events can create conditions that defy our models. This means every rocky planet, including Earth, may have experienced moments of unimaginable chaos. For decades, we saw the moon as a Rosetta Stone for planetary history. But if that stone has been altered by unknown processes, what else have we misunderstood? The presence of hematite, rust, on the moon challenges everything we thought we knew about its environment and history. The Chang'e 6 mission didn't just bring back rocks, it brought a cosmic reckoning, forcing us to confront how little we truly know. The moon's hidden, tumultuous past now casts doubt over our understanding of our own place in the universe. For millennia, the moon's far side remained a mystery, until the Chang'e 6 mission. Launched by China, this robotic explorer set out to land on the far side, collect ancient soil and rock, and return them to Earth. Communicating with the lander required a relay satellite, and Jadawanger Ogrizaro and Kekiao 2, positioned to bridge the gap between the hidden hemisphere and mission control. In June 2024, the Chang'e 6 lander touched down in the South Pole Aitken Basin, a site of immense scientific value. It was the first time any nation retrieved material from this hidden hemisphere. The lander's drill and robotic arm collected precious lunar regolith and rock fragments, then sent them back to the orbiter. The mission returned nearly 2 kilograms of material, priceless evidence from a world we'd only glimpsed from afar. For the first time, scientists had samples from the moon's mysterious other half. These rocks held clues to the moon's formation, the solar system's most violent impacts, and the stark differences between the two lunar faces. The secrets within these stones were poised to challenge everything we thought we knew about our nearest celestial neighbor. When the first Chang'e 6 samples were analyzed, scientists found something astonishing: microscopic crystals of hematite. Hematite is a highly oxidized form of iron, a type of rust. On Earth, it forms only in the presence of abundant oxygen. The moon, as we understood it, was supposed to be an oxygen-free environment. For decades, lunar rocks were thought to be chemically reducing, with no free oxygen to create rust. The discovery of hematite directly contradicted this core belief. Could the samples have been contaminated? The Chinese team took every precaution, confirming the hematite was of lunar origin. This was not a contaminant, it was an authentic part of the far side's geology. The findings shattered the simplistic view of the moon as a uniform, inert body. It suggested that, at some point, local pockets of oxygen-rich conditions existed on the moon. The moon's chemistry was far more dynamic and strange than anyone had suspected. The key to the lunar hematite puzzle lies in its location, the South Pole Aitken Basin, the largest and oldest impact crater in the solar system. Scientists now believe the impact that formed this basin created a temporary superheated atmosphere, liberating oxygen from lunar minerals. In this brief high-pressure bubble, iron particles reacted with oxygen, forming hematite before the environment returned to normal. This theory also explains the magnetic anomalies detected around the basin. Minerals like magnetite formed during the same event, permanently magnetizing the rocks. The impact left not just a physical scar, but a chemical and magnetic fingerprint that has endured for billions of years. Giant impacts, it turns out, are powerful chemical reactors, fundamentally altering a planet's surface and magnetic properties. The SPA impact didn't just reshape the moon's topography, it created minerals that couldn't have formed otherwise. The hematite, found by Chang'e 6, is a relic of this fiery genesis, a tiny crystal telling a grand story of destruction and creation. The Chang'e 6 samples revealed more than just rust. They uncovered a surprisingly active volcanic past on the far side. Scientists once thought the far side was geologically quiet, but the rocks showed evidence of 2 distinct volcanic episodes. The first phase, triggered by the SPA impact over 4 billion years ago, sent shockwaves deep into the moon, fracturing the mantle and unleashing magma. The second phase, much later, produced basalts dating to 2.8 billion years ago, evidence that the far side's interior remained hot and dynamic for billions of years. These findings explain the moon's two-faced nature. The SPA impact set the hemispheres on different evolutionary paths. The near side became a sea of lava flows, while the far side's volcanism was more episodic. The far side was not geologically dead. Its volcanic heart just beat to a different rhythm. The moon's history is far more dynamic than its cratered surface suggests. Among the Chang'e 6 revelations, one stands out. The far side is even drier than the near side. The volcanic rocks collected are the driest lunar basalts ever studied, suggesting a fundamental asymmetry in the moon's deep interior. The SPA impact may have cooked the mantle beneath it, driving out what little water was there. This bone-dry mantle is paired with another surprise. The moon's ancient magnetic field was not stable. The Chang'e 6 rocks show the field decayed, then resurge around 2.8 billion years ago, coinciding with the second volcanic phase. The moon's dynamo was not a steady fire but a flickering flame reignited by geological activity. Rising plumes of hot material heated the core, temporarily reviving the magnetic field. The moon's heart sputtered, died down, and was shocked back to life by its own internal convulsions. The Chang'e 6 discoveries force us to rethink how rocky planets evolve. Instead of slow, steady change, giant impacts can permanently alter a world's destiny, setting hemispheres on different paths. This has implications for Mercury, Mars, and even Earth, planets shaped by ancient collisions. The moon is now the primary case study for this violent process. The discovery of hematite opens new avenues for exploration and resource use, hinting at complex chemistry at impact sites. Could we one day harness these processes for oxygen extraction? The moon's rust is a signpost to a new understanding of planetary evolution. The silent gray world we thought we knew has revealed a past of fire, chaos, and chemical surprises, challenging us to look again at our place among the worlds.